Hello, this will be an introduction to Ethereum lecture. So we will start by a high level of what is a state change in the blockchain. So as you know, a blockchain is a chain of blocks. So we have here block number 1, block number 2, block number 3. And in the header we have or in this header here in particular, we have a pointer towards the previous block, right? This is just the hash of the previous block. Now we can assume that block 1 is kind of the start of the whole history, and we can say that the consensus about the current nonce at this block 1 is empty, right? There's no particular nonce, but everybody agrees that this is block number 1. So there's no state change involved here. Now, if we move forward, so let's say we move to block number 2. Then there's a consensus that needs to be reached. This is, for example, reached through proof of work. Can also be reached through proof of stake or other consensus mechanisms. And here we have then the list of possible state transitions that we can include in the block. For example, we can have transaction number 1, which says I want to transfer from address A to address B 3 coins. Right. So that's a possible state change. And then in block number 3, there's a new consensus nonce that identifies the consensus. And then we can have other state transitions, for example, a transaction that says I would like to send 2 coins from B to address C. Now, let's imagine we find now a third transaction, right? This is a new transaction that arrives. Transaction number 3, is this transaction valid, right? So think to yourself, how would you validate this transaction given the history here that you've seen? Now, basically what you can do is, you can go to, D wants to receive 1 coin from address C, right? Then we can go here to address C. We can say, it got 2 coins from address B. Oh, okay. So B has to have at least 2 coins. Okay, it got 3 coins here from address A in this particular transaction, right? And now the question is, where did A get coins from, right? So basically you can ask yourself here, is this really a valid transaction? And it would be valid if A got coins at the beginning, right? So another way to store data in a blockchain is to store explicit state. So again, we have here transaction number 1 and transaction number 2. But now we also store a state commitment. And the state commitment at the very beginning here is A owns 50 coins. Right? And if A owns 50 coins in the first state, then in the second state, because it transfers 3 coins to address B, it will have 47 coins, while address B increased to 3 coins. And the same goes for then block number 3. You have another 2 coins that are transferred from B to C. Okay, so what are the advantages of explicit state storage? So if you're a light client, or if you're basically somebody who doesn't want to go through the whole history as we have just done, then if you trust the state representation, you can basically just look at this and say, I know B has 1 coin at least, right? So if you see a new transaction that transfers 1 coin from B to another address, you know this might be a valid transaction because there are enough coins in the account of B. And the convenient part here is that you can really verify a sequence between any 2 blocks, right? You don't have to go through the whole history. And overall, this is really helpful for light clients that need to sync up quickly. So Ethereum is really that. It's a replicated state machine. So state machine is what we just said, right? Here, this store state. Replicated because it's a blockchain which is distributed on many machines, right? It's basically a distributed network, a distributed database that's stored on thousands of so-called full nodes. Bitcoin is in a sense nothing different, right? There's nothing novel on the blockchain side in Ethereum itself, right? Both are blockchains. and also and Bitcoin as well stores state, as we've seen in the previous lecture in the UTXO set. If you in Ethereum you have a bit a more flexible programming language, as we'll see later. So Ethereum was introduced in this yellow paper here by Gavin Wood, which is actually a spectacularly well done specification of Ethereum. So it contains all the details that are necessary to implement like a basic client, I would say, almost. It contains a lot of details about the so-called Ethereum virtual machine. If you're interested in the later details, we also have a lecture covering this particularly. So it's a really well done work, I have to say. So you can think of Ethereum as a slow and expensive world computer. Slow because blocks are updated on average only every 12 seconds, right? So you have a 12-second block interval on average. Expensive because you have to pay gas for transactions. So there are certain transaction fees, and this does cost gas. And it's a world computer because it's a distributed network across many machines out there, which can be used by anyone. Now, the beautiful thing is that there's consensus among all nodes about the execution, right? So this is exactly what smart contracts need, and it has a more flexible transaction. It has more flexible transaction types than Bitcoin. If, for example, it does have loops, right? So you have things like while or for loops that you can use if you want to. So it's a quasi Turing complete language. So it's only quasi because if you run out of gas, so if you run out of fuel or fees to execute a contract, then your contract is halted, right? So your smart contract will stop executing at that point in time. And that's why we say it's only quasi Turing complete, because the execution could halt at any point in time due to this restriction of transaction fees. Now, a replicated state machine can be modeled as follows, right? So you have a possible set of states that we denote as S. You have a set of possible inputs I, and a set of possible outputs O. And what you do is you apply a transition function F, right? So you have a state, you apply an input, right? And this basically brings you to a new state with some output, right? So you can think of the input as arbitrary programs. I mean, these are basically transactions, right? And the start state here is the genesis block, or the block 1 in our previous example. The transition function F executes those programs. So this means an execution of a program means you change the state from one state to another. Here we're going to look now at the different states on inputs and transition functions, how they are actually encoded in Ethereum. So the state itself is basically a map from an address to the state of that particular address, right? So in Ethereum, or in Bitcoin as well, addresses are typically denoted with a hexadecimal sign at the beginning. So it's, for example, 0AX, and then it can be beef, 0, 1, 2, 3, etc. So these are hexadecimal numbers. And this address here in particular, it has then basically some state, so it can have code. So this is EVM bytecode. It can have storage, so these are variables basically that you can store. It can have a balance, and this balance has to be denominated in Ether, because that's what the Ethereum blockchain wants to. And nonce is the number of transactions that were sent by this address, right? And this has to be strictly increasing. So every time you issue a new transaction from this particular address, or every time this is issued from this address, this nonce is increased by 1. On the input side, we have transactions. So the input modifies the state of this particular address, and the inputs specify an address from which this is sent. You have a signature, right? This is generated with your private key. So an address here, an address has always is basically a public key, which is derived from a private key, right? And in order to spend coins, you need to know the private key. And here, this is where the private key produces a signature for this particular transaction. So nonce you can think of an incremental number that's incremented by 1 each time you perform a transaction. 2 is the address that you want to spend to or call. Data is the particular data that you want to pass. For example, it can be you want to call the function f with the value 1. This can happen, right? If you want to call a smart contract, you can call its particular function and pass it some data. And here value is the value in terms of ether that you want to transmit within this particular transaction. So we'll go into details of what the gas limit and the gas price is. I'll just give you here a high-level intuition. So gas limit is the total gas that you want to spend, right? And this is kind of the maximum that you want to spend. So if you reach the gas limit, then the execution of this transaction halts, and this input will not modify the state of the Ethereum virtual machine. Gas price is how much ETH you want to pay per gas. So gas is paid in ETH, that's just a price tag. Okay, so the transition function f here, basically what it does is it validates the signature of the transaction. So it validates whether you actually have the correct, you know the correct private key, and whether the nonce was properly incremented, right? If it wasn't incremented, then you can't execute a transaction with the same nonce as before. And then you basically execute the code, right? So you take this data, and for every byte code that you execute, you calculate how much gas did I use. I mean, you don't do this, as the blockchain is doing it, but you use like gas plus 1, plus 2, plus 3, etc. And if you reach the gas limit, you just stop, right? And otherwise, you successfully finish, and you pay basically here this amount of gas to the miners. So the miners are those that are rewarded for mining a transaction in the block. Obviously, the start state of the Genesis block is empty. There's basically no particular transaction being done. It could be that some addresses are granted some Ethereum at the beginning of the blockchain, or in general, if you start a blockchain, then you can grant several coins to some initial addresses if you want to. That was, for example, not done in Ethereum.